this notion of cardinality. So, as is my wont, I am going to ask a pop quiz. And for usual, I'm not going to collect it or anything, so go have something to write on. Doesn't necessarily have to be like a clean piece of scratch paper. I guess I should put it in water. Well, that's x and y. We say the cardinality of x is the same as the cardinality of y if. Finish that sentence. Cool. And like with most of these, just do you know the definition? Either you kind of knew it or you didn't. So I'll give you like, not long. It's give it nothing like 5 seconds if it looks like people are still hiding. Then we'll see how we feel. Finish that sentence. Bijection from where to where? I mean, I guess like, I'm not collecting that because finish this off. All right. So let's hear it. We say two sets have the same cardinality if
there's a bijection between them.
And that's a perfectly fine way of saying it. I'll say from x to y. Not for any big reason, like what you wrote was perfect. Cool. And let's see, I don't think I'm introducing a definition today that I want to replace this pop quiz question. I am introducing a new definition. So I guess we'll ask this again at the start of Friday. Sound good? Or maybe I'll change things up and switch back to the epsilon delta definition of a limit. Epsilon n definition of the limit of a sequence. So, with that being said, let's maybe even put that down. Two sets have the same cardinality if there exists a bijection from x to y. And right, so what's the idea behind that bijection? So two sets have the same size if you can list the two sets at the exact same rate is how you should think of it. So this bijection gives you a rule that takes a single element of x, gives you a unique element of y. So you can like line up the elements of x with the elements of y using this bijection. And for a finite set, that's not so exciting because if two sets both have 12 elements, then there's a bijection between them, but they also just have the same size because they both have 12 elements. Something interesting happens once you have infinite sets. As we saw last time, there are some surprising sets that have the same size. So if you take the set of natural numbers and the set of even natural numbers, those are in bijection. They have the same size as each other. Even though obviously there are a few even natural numbers than there are natural numbers. So you can like throw out half of an infinite set and it's still the same size.
And the bijection was that was just like n goes to 2 times n. If you take a natural number and multiply it by 2, that gives you an even natural number. Oh yeah, natural looks like an obviously injective because you can divide by 2, and it's surjective because even things are multiples of 2. We established that the natural numbers have the same size as z. For that, the bijection was a little bit more complicated to come by. I think what we settled on is 1 goes to 0, 2 is going to go to 1, 3 is going to go to -1, 4 goes to 2, 5 goes to -2. So you just start listing the positives and you shuffle in the negatives. That gives you a bijection. And I think checking the details that function is bijective was like homework, right? It's not necessarily a super hard homework, but maybe it's a little bit tedious and you have to be careful checking the details. It turns out there's some even bigger sillinesses that happen. If you take the naturals and compare it with the naturals cross the naturals, those are in bijection. Naturals in Q, those are in bijection. And that made me think, well, that just means that like all infinite sets are n. But that turns out not to be the case. The real numbers are strictly bigger. The real numbers are infinite, but they're an infinite that's bigger than n. So what I want to do today is walk with the idea of sets that have the same cardinality as n and figure out like what are easier ways to prove that a set has the same size as n than just finding a bijection. Because it turns out, in the case of n, we can prove some things that say that you don't need a bijection. You can get something weaker. Cool. So, let's do it. So here's the new definition of the day. A set X is called countable if either it's finite or it has the same cardinality as n. So a set is countable if it's either a finite set or if it's in bijection with n. And the reason we call those countable is you can like count them. The bijection with n kind of says that you can pick out a first element and then a second element and a third element and a fourth element and so on. So you can count sets. And finite sets, well, you can obviously count the number of things in those sets. They're only finitely many. So that's the motivation for the definition. A set is called countably infinite if it is countable and not finite. That seem like a reasonable thing for that to mean? Yeah. Countably infinite means countable and infinite. A set is called uncountable, or sometimes uncountably infinite, if it's not countable. Hopefully that seems like a sensible definition too. Sometimes countably infinite in the literature, you'll see it called like innumerable, because you can like number the elements of the set one at a time. So here's what I want to do today. I want to talk about what sets are countable. And in particular, we have these like loose ends that those two sets are countable. I want to try to prove that. And to do that, we need to like say some things about the natural numbers. Here's the first one, which hopefully is like intuitively true because we're not really going to prove it. Lemma. If U is a subset of n, then U is countable. Hopefully that seems like believable. We don't really have the tools in place to prove that rigorously. Because to really prove that rigorously, you need to like know what the natural numbers really mean. And to do that, like, so you know how we have like the axioms for the real numbers? There's a similar set of axioms that give you the natural numbers. They're called the Peano postulates. Sorry, Peano. I'm North American, so I'm not going to pronounce any European name correctly. So here's like a very intuitive one. So since U is a subset of the natural numbers, we can list it in order from smallest to largest. We can list U as smallest element, comma, second smallest element, third smallest element, and so on. That seem believable? Oh, and like one of two things either happens. Either that stops, and we run out of space, and then U is finite. Or we keep going forever, but then we can define a bijection from n to U, sending n to the nth element of the set U. That seem like a bijection?
So justifying that takes some work, but we won't. So there's something we will just have built in.
Any subset of the natural numbers is countable. You might interpret this as saying that n is the smallest infinite set.
In that, like, I haven't talked about how to compare sizes of infinite sets. I just talked about, like, when they're the same. But something like a subset size should be less than or equal to the big set size. If that means anything. I haven't said what it means. So there's, like, the intuitive thing. If a thing is a subset of the natural numbers, either it's just finite, so it's slightly smaller than all the naturals, or it's the same size. Cool. So all that is stuff that we'll assume without clue today.
Here is what I want to prove. For any non-empty set X, the following are equivalent. Either X is countable, so it's either finite or it's in bijection with the natural numbers. That is equivalent to the line that there is an injective function f from x to n. Oh, so that's weak R, right? I just need an injection to get to countability, not a bijection. Or there's a surjective function from n to x. And that's kind of like, each one of those also says that, like, the set has size at most as big as n. So let's kind of try to look at that. So what does it mean for there to be an injection from x to n? Well, it means I can take x, I can map it into n, and like if there's all of x and there's all of n, then like I only use up some of n. And that's like a meaningless picture. But I have a map from x to n that only hits some of n. Yeah, that seems like x is smaller than n, right? Whatever smaller means, it should account for that. If there's a surjection, then I have a map from n to x. And if you take everything in n, it hits everything in x, but it might hit some things more than once. So that certainly sounds like n is at least as big as x. So in each of those cases, we get this line that says if anything is at most as big as the naturals, then you can find an injection from that set to the naturals or from the naturals to that set. Feel pretty good? So let's try to compose some proofs. And each one of these will be reasonably light. So whenever you want to prove three things are equivalent, you just want to have a path of implication that starts at any one of those items and goes to any other. So it's kind of like go through the macro look at the proof and see how the logic's going to go. It looks like the first thing I'm going to do is claim 2 implies claim 1. Then I'm going to prove that 1 implies 3. Ooh, notice that means that 2 implies 3, doesn't it? So I don't need to prove 2 implies 3. The only thing I still have to prove is 3 implies 2. If I can do that, then I can go from any of those claims to any other. So there's the strategy I'll use. Let's try to do it. So 2 implies 1. Let's let f from x to n be an injective function. So here's the idea that I'll use. By restricting the codomain, f from x to f of x is a bijection. Do you think you could convince me of that? What does it mean to be a bijection?
There is a second verse.
Oh, sure, that's one. I'm going to go for the other definition. I think that'll be easier this time.
Onto and 1 1.
Onto and 1 to 1. Let's try to prove that this function with the codomain restricted to be the image is onto and 1 to 1. And I think onto is the, well, they're both pretty quick, but onto I think is the one that's most immediate. How do you show something is onto?
Proof the output as opposed to the input.
Yeah. Everything in the codomain has an input. So
f is, let's not use 1, a. f is onto. So I need to show that everything in the codomain is hit by something. So let's let y be in f of x. What does it need to be in f of x? What's the definition of f of x?
Every element in X, I'll get into the function,
Yeah, so there's the definition of f of x. So if y is in that set, it has to have this form.
So y equals f of x for some x in x by the definition of f of x.
Ooh. Does that definition just hand me what I wanted? Yeah, so that's something you can always do. If you have a function and you want it to be onto, just change the codomain.
So f from x to f of x is onto. Step B.
Tell me, why should this function be one-to-one? Or the objective, whichever I went. Yeah, we assumed it, didn't we? I guess we assumed it with a different codomain, so it's like write down the details, but I think it'll basically be what we assumed f is one-to-one, changing the codomain doesn't change that.
So if x and y are in x and f of x equals f of y, then since f from x to n is one-to-one by assumption, x equals y. F of x equals f of y, f is one-to-one, so x equals y. Oh, cool. So like, changing the codomain doesn't change if a function's one-to-one or not. Oh, so are we done? Well, are we done justifying the claim? Well, that this is a bijection? I think so. We have a bijection between them, so they have the same cardinality. So the size of x is equal to the size of f of x, but f of x is a subset of n. This lemma says something now, doesn't it? What does it say?
f of X is countable.
Which means either it's finite or it's in bijection with the naturals. So I have a bijection from x to a countable set. So what can I conclude about x?
Countable.
Also countable. Oh, cool. That just does it then, doesn't it?
And there's going to be stuff on the next page for 1 implies 3. But 1 implies 3 is also, well, every one of these is like pretty quick.
So let's sketch it here just for practice composing a proof. And then we'll talk on the next page. So if you want to prove 1 implies 3, what do you get to assume?
That X is countable.
What is the goal?
There's a surjective function from X of X.
And I'm going to use some notation that I haven't used at any point in the past. The arrow with two heads is commonly used as shorthand for a surjective function. Since this is just scratch work, that's fine. All right, so there's the assumption. We have that as the goal. How do we go between? What intuition do you have about what seems like it might be useful?
So definition of countable, that X is the same cardinality as
Or it's finite. So I see like an either or case, so maybe cases are in order. So in case A, which is like the main case anyway, finite sets are kind of boring from the point of view of doing analysis. And that you can like, do it more or less easily. You don't need to be, whatever. Let's suppose that X is in bijection with N, well, has the same cardinality as N. What does that mean? Cool. And it doesn't matter which way we write it. It could go from N to X or X to N. It would mean the same thing. Oh, are we done? Yeah, because what is a bijection? Injective and surjective. In particular, it's surjective. Case B. X is finite. How can you write a surjective function from the natural numbers to a finite set? So maybe I'll propose like a finite set is a set that has like n elements for some n. So I can list them one at a time. So now, let's try to come up with a map from n to this set. Where would you want 1 to go? How about x1? Where do you want 2 to go? So that'll get me covered all the way up through n in the naturals. Where would n go? There's an n plus 1 though. Where do you want that to go? There is no xn plus 1. x1. How about x1? xn plus 2? I'm going to be lazier. Let's send it to 1. Because if I already hit everything? Yeah, so who gives a shit if I hit the same thing twice? It doesn't need to be an even cover or anything. It just needs to hit everything. Anything bigger than n, where do you want to send it? X1. Your thing would walk 2, but then I'd have to think about modular arithmetic, which I guess wouldn't be a disaster, but I don't want to think about modular arithmetic right now. Oh, cool. Does that give me a surjection? Oh, nice. So I'm done in each case. Let's write it down. Assume that x is countable, so either x is in bijection with n or x is finite. If x has the same cardinality as n, then, well, I don't know, do I actually need to say anything more? Or should I just be quiet and let you fiddle and flip? Should I say anything right now? Okay, yeah, I will. If size of x is the same as size of n, then what can you conclude?
It's a bijection.
By the definition of cardinality, there exists a bijection. There is a, so I don't need the there exists symbol. Bijection from n to x. Explain why this gives the desired result. So, we have a bijection from n to x. We want a surjection. Why is a bijection something that makes us happy?
Because a bijection is surjective and objective.
Yeah. Every bijection, and I'm just going to be forgetful, is a surjection by definition. Nice. On the other hand, we may list the elements x as x1 through xn. Let's define a candidate surjection, and I don't think I'll even check that it is a surjection. So I think there were like two cases. When k is less than or equal to n, let's define g of k to be, I guess to the previous page while you were jotting down notes, what did we set those to be?
K to A, K to X and G.
Yeah. When k is bigger than n, let's define g of k to be, what do you want to define g of k to be when k is bigger than n?
K to X1.
Sure. And right, like, basically it doesn't matter how you define it when k is bigger than n. Like, you could have used this modular arithmetic thing and it would have been correct. Neato. Does that complete the proof? Either way, we get a surjection. 3 to 2. So, this is the one that will involve like a weird bit of set theory. So, I think here's how we'll try to come up with a plan. So let's let g from n to x be a surjection. So 3 to 2 is if there is a surjective function from n to x, then there's an injection from x back to n. So let's let g from n to x be a surjection. So from n to x, I have a surjection. I want to come up with, and I called that g. I want to come up with a function that goes the other way. And here's how I will try to do it. So let's pick some x, little x and big X. I need to find a way of mapping that thing back to n in a way that makes sense and uses the assumption. And I think here's the idea. Is that x hit by something? Yeah, it's a surjective. G is a surjective function. There's some n that goes to x. So for each x, let's just take like maybe the minimum n that goes to that x and define that to be g f of x. That seem like a reasonable plan? Does that seem like it'll be more or less obviously one-to-one? Yeah, take two different outputs. If they result in the same, well, two different things down here. If they result in the same value up there, that would give me, two different values up here. Nope, if they give you the same value, that one value would have to go to both of those outputs. Oh, so that would mean g isn't even a function. That would be bad. So let's just put that into WADs. So let's let g be a surjection. We need to come up with an injective map. For any x, so let's put this into WADs first. Explain why g inverse of x is not the empty set. Tell me why g inverse of x has something in it.
Because g is not that x is placed on that.
Yeah, let's write that down. Since g is onto, let's let x be in big X, since I want to prove something is true for every x. Since g is onto, there is some n with g of n equal to x. All right, cool. So why does that mean g inverse of singleton x is not empty?
Because the inverse must be n. Some x must be
not the empty set, it has to have an element. Based on what's written already, like, do you know something that's in that set? Yeah.
Are you still by contradiction?
Oh, yeah, we can do that. Let's change horses midstream. That's a saying that I heard somewhere as a bad idea. Let's do it. So let's change to a proof by contradiction. If you have a direct proof in mind, like, finish it up. Maybe we'll do both. By contradiction. So let's suppose G inverse of singleton X is the empty set. How can you take advantage of that? Ooh, let's see that. So that would mean G of G inverse of X equals G of the empty set. That's probably still the empty set. Have I made you prove that the image of the empty set is the empty set at some point? That would make a viable benchmarky thing, because you'd have to unpackage some definitions. Anyway, cool. How does that help you?
We can simplify the left side down to just X.
No, not quite. You don't know G is a bijection. So like taking the inverse and then making it bigger can like change things. Here's something that you definitely have proved. This is equal to singleton X intersect the image of G. That's something that I had to prove. What is the image of G, though? What's the assumption about G?
Goes from N to X.
Goes from N to X. And what type of function is it?
Surjection.
Surjection. So what is its image?
X.
All of X. So G is onto. So this is equal to X intersect the set big X. And if you take singleton X intersected with the big set big X, what do you get?
Singleton X.
Just singleton X. Oh, is that a contradiction?
Yep.
All right. Yeah, I guess we do get a contradiction that way. I buy that. I'm going to finish the direct proof too now because like there's something in that space. Because like there's only one sentence left also. Right, what does it mean to be in the preimage? It just means that G of n is equal to that X. So that n is in G inverse of X. So G inverse singleton X is not empty because it has an element. Does that feel pretty okay? So like the contradiction proof is definitely not a wrong proof. I think it's a proof that's more complicated than the direct one this time. We feeling pretty good? So we have that the preimage is not empty, and the idea we kind of sketched off to the right is, well, let's just send any element of the set big X to something in the preimage. There's something in the preimage, let's just pick a thing. Consider any x and x to define f from x to n. Let f of x be any fixed element of G inverse of x. I'll let you decide how you pick the element. There's something in there, just pick an element. You want to take the minimum? Take the minimum. Let's explain why f is 1 to 1. How do you show something is 1 to 1?
everything in the code already has a unique input in the domain.
Except that some of them might not have any inputs that go to them. You don't know it's on to. So instead, think from the point of view of input values. There are no two distinct input values that both go to the same output value, which is similar to what you said, but I don't know that every output value is even in. So that's what I need to show. I need to show there are the two equivalent definitions of what it means to be one-to-one. So, either I assume that you have two distinct input values, or I assume that you have two input values that both go to the same output. Which one would you rather use?
Second.
Let's use the second. They'll both be similar, but like if you pick the wrong one, sometimes it's a little bit more work. And the way you can tell is once you're done with the proof, if you like assume for the sake of contradiction that that f of p is not equal to f of q, then you may as well have just done the second one. So let's let p and q be in the set big X. Let's assume f of p is equal to f of q. Maybe I'll even give it a name, n. Then let's try to get a contradiction. Or not a contradiction. Let's try to show that p equals q. And the only way I can do this is by like using the definition of f somehow. What is the definition of this function? I defined f from x to n by saying f of x is an element of g inverse of x. So n equals f of p means, what does it mean? So the definition of this function says that to define f from x to n, let f of x some element of g inverse of x.
That means n is in the
Yeah, but p instead.
Yeah.
N is in g inverse of singleton p. Ooh, so let's unpackage this a little bit. N is in g inverse of singleton p. So that's like a pre-image statement. What's it mean to be in the pre-image? Yeah, so you already have the p. So n is in g inverse of p means that g of n is in singleton p. But what's the only thing that's in singleton p?
P.
P. So what do you know about g of n? Equal to p. So g of n equals p. Oh, but I also have the same thing with q, right? Similarly, what else could I conclude about g of n being equal to? Because of that. Q. All right, so what can you conclude?
P is equal to Q.
P equals q. Is that what you wanted to conclude?
Yeah.
Yeah. So this sucker is 1 to 1, and you're done. Groovy. That feel pretty good? And I think we can address at least one of the two examples of really big sets. So if I want to show that n cross n is countable, I just need to find an injection from n cross n back to n. And here's how I'll do it. I'm going to use the prime factorization theorem, which is in fact really one of the Peano postulates. So let's write it down. So the prime factorization theorem says that there is a subset, 2, 3, 5, 7, and so on, called the set of prime numbers, satisfying the two conditions. Any natural number k can be written as a finite product of primes. So k can be written as the product from n equals 1 to n of a bunch of powers of primes. That's just true, right? 54 is equal to 2 times 3 cubed. There's a product of the power of primes. It's also unique. If you've written something as a product of powers of primes in 2 different ways, those 2 ways have to be the same. That's not something we'll try to prove, because that's just something about the natural numbers. If you take a class on number theory, you'll see this done rigorously. All right, so with that built in, I'm ready to define an injection from n to n cross n. So proof that size of n is equal to size of n cross n, we will define a function phi from n cross n to n, which we will then show is injective. If we can do so, then by lemma 4.2.3, the lemma we just finished proving, we'll be done. Feel good? All right. I guess so what we'll know is that n cross n is countable. But countable means either finite or in bijection with n, but it's not countable. It's not finite, so it's got to be in bijection with n. So let's define phi. So I want an injective function from n cross n to n. Here's how I'm going to propose doing it. Let's define phi of a comma b to be 2 to the a times 3 to the b. With the prime factorization theorem, you think you could just show that that's 1 to 1? Should we do it for the sake of just practicing showing something's 1 to 1 once? Yeah, let's do it. So I want to show this sucker is 1 to 1. So let's let AB and CD be elements of n cross n. Let's assume phi of AB equals phi of CD, and see what we can do. Right, so that's how many of your proofs of 1 to 1 just should start. Consider 2 different elements of the domain. Assume that they go to the same place in the code. And now we'll just mess around. By definition, what is phi of AB? Same thing with the other one?
Yep.
So 2 to the a times 3 to the b equals 2 to the c times 3 to the d. Two and 3 are prime, right? So what does the uniqueness part of the prime factorization theorem say?
It's only one way to.
Mm-hmm. Yeah, so there's only one way to write a thing as a product of primes. It looks like here are 2 different ways to write the same thing as a product of primes. So there's only one way, so those 2 different ways of writing this thing as a product of primes have to be the same. So what can you conclude?
those are the same factorizations. A is equal to the power law 2 on the other side. Same thing with the powers on 3.
Oh, cool. Does that just like do it? Thus, AB equals CD, and phi is injective. Cool.
All right, let's make some progress on this next one, because I think I've got some time. So, that was one of the surprising, really big countable sets. The natural numbers are a really big set, but they're in bijection with the natural numbers, which is like really surprising. The same can be said for Q. And this is going to use the same idea. I'm not going to try to find a bijection from N to Q. That's too hard. By this theorem I have, if I can find a surjection from a known countable set to Q, then I win. And here's the known countable set I will use. I will try to find a surjection from Z cross N to Q.
What's Q again?
The rationals.
So,
let's try to do it. So, I know that the size of n is the same as the size of n cross n. By this proposition, which isn't so hard, and I've listed as like an extra credit at the end of the homework posted for today, so you can get 200% on today's homework. The size of n cross n is the same as the size of z cross n. In particular, that sucker is countable. So, let's do it. Let's define f from z to n to q, z cross n to q by the rule f of m comma n equal to m divided by n. Oh, is that like more or less obviously onto? I guess let's try to do it. How do you show that anything is onto? You have to consider anything in the codomain in the target set and show that it's actually hit. So let's consider any P over Q in Q with P in Z and Q in N. Right, you can always arrange that the denominator of your fraction is positive. That's all that that's doing. All right. So for that particular P comma Q, what does F send to it? What does F send to that? Yeah. How about P comma Q? Cool. So I am in fact at time. I think I'm going to stop here. We're going to pick up right there and just finish writing that proof. You have everything you need to finish writing that proof already. So what might be a nice idea is just to start tomorrow already knowing what's going to go. So finish writing up that proof. We'll start on it next time.